Okay, so now let's try to go to what you are familiar with, maybe, what you have seen in your elasticity courses, is the inversion. So this is an equation that provides the stresses in terms of the strains, okay? Could be this equation inversed. So could we obtain the strains in terms of the stresses? Well, they can. So why? Well, we have to do some algebraic operations. What is the way of doing that is also detailed here, no? For instance, from here, I can just isolate the strains and obtain the stresses as the strains are 1 over 2 mu of the stresses minus this term. But this term still depends on the stresses, on the strains. Okay? So before proceeding, we have to solve for this term, express this term, trace of epsilon, in terms of the stresses. So for doing that, we take that's the trace of that. The trace of this is the trace of that. This is a scalar, so those goes out, plus the trace of 1. The trace of the tensor 1 is what? The sign of the diagonal terms, so it's 3. So 3 lambda trace of epsilon plus the trace of that, which is 2 mu trace of epsilon. So it's 3 lambda plus 2 mu trace of epsilon. So now can replace that expression, first we solve trace of epsilon as this term that goes to the other side, 1 over 3 lambda plus 2 mu times of sigma, and now we replace that term into that term. And finally, after some operations, we obtain that. So this is the inverse elastic constitutive equation. If that was the equation that provides the stresses in terms of the strains as one term that multiplies the unity plus one factor that multiplies the strains, now we obtain the strains as one term that multiplies the unity plus the unit tensor plus one factor that multiplies the stresses. So, well, let's do a change of variable, so to speak. Let's define 2 new coefficients, E and nu, in terms of the Lamé parameters lambda and mu, that make this equation simpler. Okay? So that is what we do with the 2 new coefficients. That is already familiar with you, right? This is the Young modulus. That is already familiar to you, Poisson ratio. Okay? So now that they appear in that equation here, like just some appropriated change of variable, defining them in terms of lambda and mu, and of course these equations can be inverted and define lambda and mu in terms of mu and epsilon. Okay? And by the way, mu sometimes in engineering concepts is also termed G, denoted by G, capital G. Also the shear, and you understand why, the shear modulus. Okay, so by introducing this lambda mu into this equation, that inverse constitutive equation, elastic constitutive equation for isotropic materials, looks simpler, looks that way. Epsilon equal minus nu over E times trace of sigma times the unity plus 1 plus nu over A, which by the way 1 plus nu over A is 2 over j, 1 over j times sigma. Or in components, we can just, this compact form, just write it in terms of the components, and epsilon ig has this formula, etc., etc. Okay, that is the inverse Hooke's law. Is the inverse of that one. Is the inverse of that one. Okay? Now, in terms of lambda mu, we just define this law in terms of the Young modulus and the Poisson ratio, which, by the way, can, once we know them, provide lambda mu. If you have epsilon and nu, the Young modulus and the Poisson ratio, and you want to compute the lambda and mu, the Lamé coefficients, just replace here. Okay? And then, whenever I send a specimen of concrete, of steel in my work to the lab in order to test these properties, they should identify the Young modulus and the Poisson coefficient, the Poisson ratio, and from that, of course, I can obtain the Lamé's coefficients. Okay? By the way, this is such important law that I'm just accepted to do what I don't do never, which is just writing these equations component by a component. So how do they look these equations in a XYZ coordinate systems? Look like that. The axial strains, what we call, when we talk about the strains, the strains in the diagonal of the strain tensor, which could be interpreted, by the way, as the unit elongations in directions x, y, z, look like that. The inverse of the Young modulus, and here there is a recursive way, sigma x here for epsilon x, sigma y here for epsilon y, sigma z here for epsilon 0, minus nu times the other two stresses, sigma y, sigma z here, sigma x, sigma z here, sigma x, sigma y here. That is a way that said that the strains epsilon x, epsilon e, epsilon z can be obtained directly from the stresses sigma x, sigma y, sigma z. What about the tangential strains? When I put here the tangential strains epsilon xy, epsilon yz, epsilon xz, by the way, you remember that they can be related to the engineering strains, what we call the angular strains, right? That were twice these strains, okay? So by the engineering strains, gamma xy, gamma xz, gamma yz, turn out to be just 1 over g, the shear modulus, times tau xy, or times xz, or times tau yz. So that also indicates why this is called the shear modulus. Because the shear stresses are obtained by multiplying this G modulus times the angular strains. Okay? So this is the way that maybe you recognize. You recognize this formula now? Have you ever seen that? This is the formula that comes in many of elasticity books. But this formula comes up from other places, comes up from all the theory that we have visited so far. And this talks about two parameters, E and G, or E and nu, they can do independent, which are two elastic parameters that have to be identified in order to characterize these equations or their inverse. And what makes us able to compute the strains given the stresses, or the stresses given the strains. Okay? What is the Young modulus? Well, the Young modulus, which are related to the Lamé coefficients in that way, is a measure, in some way, the measure of the capacity of the point or the material to produce deformations when he's subjected to strains in a given direction. So, in other words, now we are going to see it more clearly. If you have a large Young modulus and you produce a certain, apply a certain stress, the corresponding strain in the direction, so the elongation, unit elongation in the direction, is smaller if E is large and larger if E is small. Or in other words, to produce a certain strain, if we have a larger Young modulus, we have to place a large stress. And if E is smaller, then we have to produce or to place a smaller stress. So somehow the Young modulus talks about the stiffness of the material in front of a certain direction, okay, to produce direct stresses, in uniaxial stresses in terms of uniaxial elongations. Of course, since the material is isotropic, this capacity is independent on the direction. Okay. What about the Poisson ratio? Well, the Poisson ratio says something different. Now we are going to see it, but let me anticipate that the Poisson ratio says how much is the cross-sectional elongation, unit elongation, when we produce a certain directional elongation in that direction. So let's see that in more details. Okay? Let's consider that problem in which we have this part here, which is subjected to just a uniaxial stress. Let's assume that the uniaxial stress follows the direction of x, that is x, that is y, that is z, so that the remaining stresses that we are imposing in this part is zero. Only uniaxial stresses. So let's see now what is the Hooke's law returning in terms of the strains of this part, of this specimen. Okay? Let's see, and we'll comment the results for two specific cases. Nu is equal 0 and nu equals 0.5. Let's see what happens. So, look, here we have the Hooke's law. Okay? So, since all the stresses are 0 except in sigma x, what we can say? That epsilon x will be 1 over e sigma x, this 1 is 0. Epsilon y is minus mu sigma x divided by e. Epsilon z would be minus nu sigma x divided by e. And tau xi, tau xz, tau yz will be 0. Because then gamma xy, gamma yz, gamma xy will be 0. So this is the result we have. But what about if we have nu equals 0? If we have nu equals 0, epsilon y is equal to 0. Epsilon z is equal to 0. So look, in that case, the deformation, the form shape of the specimen would be like that. So there will be an elongation in direction x, an extension, but then in the directions y and z, in the other directions, there will be no contraction, no elongation. You see? Because epsilon y and epsilon z is a 0. And also the shear strains will be 0, so the angles won't be modified. So typically, in that limit case, the deformation would be just, the strain will be just in the one direction, and so as for the corresponding deformation. Okay? No contraction of the cross-section due to this stretching. Let's now consider another case. For instance, nu different from 0, and specifically nu equals 0.5. Well, by replacing it to here, then epsilon x would be 1 over epsilon times sigma x, as before. But now epsilon y and epsilon z, since nu is now different from 0, will be negative. Look, negative, because there is a minus here. There is a minus. So epsilon y and epsilon z would be equal to each other, proportional to sigma x, and 0 and negative. Look. So that means that there will be a contraction and negative elongation in the cross-section direction of this part. So that's what is specified here. In the direction y and z, the element, the material will shrink in a way that is proportional to the Poisson ratio. So we see the role of the Poisson ratio. It's just determining that under a certain strain and a certain uniaxial stretching in that direction, how much will the cross-section, in the other two directions, will shrink due to that. And look that for nu equals 0, this shrinkage will be 0, but for nu equals 0.5, that shrinkage will be relevant. And look, there is another property here. For nu equals 5, what happens if we take the trace of epsilon x, epsilon y, and epsilon z? How much is the sum of this? Do you realize that it's 0? 0. What is the implication of that? You remember that the volume deformation E, which is the increment of volume per unit of volume, is in a small strain theory is the trace of epsilon. So there is no volumetric deformation. That means that the volume is kept the same. In other words, the volume that, so to speak, we gain here is the same that we lose in the other directions. So this is that the material behaves incompressibly. There is no change of volume as the material, that means that the material is incompressible. So the way of representing an incompressible material in linear elasticity is just by putting nu equal 0.5. Okay? If nu is equal 0.5, then the material behaves incompressibly. If we produce an elongation in one direction, that is what we would have here, then we have a reduction in the other two directions, so as the amount of material, of volume, is the same. Okay? It's the only case in which this happens. Because you understand that for nu equals 0, since there is no shrinkage, we increase the volume. Okay? And we change the density, but since the strains are small, this decrease of density is negligible, so we always consider density has not changed. But this is important because we realize that nu equal 0.5 corresponds to an elastic material which is incompressible. And there are some of them. For instance, typically, what is the value of nu? Maybe you remember that, or you should remember that. You are a structural engineer, you are engineers. What is the typical values of the Young modulus and the Poisson ratio for concrete and steel? Can you remember? In pascals or megapascals?
30 gigapascals.
30 gigapascals for
the
concrete. Then steel is how many times? Typically 10 more times. So 300, 200, depend on the steel. And what about the Poisson ratio? 0.2 for concrete, and for steel? No, 3. Never 0.5, because, so, that's a way to understand the role that the material properties do on the material. Look, if epsilon is large, the strains for the same stress is small, so this elongation would be small. We said that the material is stiffer, okay? The material deforms little when we apply in stress, okay? So E plays a role in the stiffening, a fundamental role in the stiffening, in the stiffness of the material. And nu, the shear, the Poisson ratio, plays a role in the volume change of the material. To the point that for nu equals 0, there is no volume change. For nu equal 0.5, we will see now that this is a limit case, the material behaves as incompressible. Okay?